Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 20, and we are entering chapter 4, which is a complete randomized block design model, or ANOVA. So let's get started. So CRBD stands for Complete Randomized Block Design. So what we're going to do is we're going to block a factor that we cannot control long term, but that we can short term, and this is going to be called a nuisance factor. So let's define a nuisance factor. When people hear this, sometimes they misinterpret it as something that's not important, and that is not true at all. It's just that we know that we can't spend the effort on controlling this factor, or that it doesn't benefit us to do so, at least in the experiment we're conducting. So the definition of a nuisance factor is a design factor that may have an effect on the response variable, our outcome, that we're not interested in studying. So I'll give you an example here in just a minute. Now, randomization is the design technique that's used to guard against such a lurking nuisance factor. Okay? So there's two main types of nuisance factors. There's the known but uncontrollable, and that will require a different analysis called analysis of covariance, which we're not going to talk about right now. And then we'll have something that's known and it's controllable, at least it's controllable short term, okay? And so the technique we're going to use for that is called blocking, and this systematically eliminates the nuisance factor's effect on the statistical comparison between the treatments. So we're wanting to compare treatments, not whatever this other factor is. So we use blocking to basically eliminate its effect on the analysis. So here's an example given by the textbook. We have a metallurgical engineer, and they want to study the effect of two different types of tips on a hardness test machine. Now, a hardness test machine, what it does is it has a metal rod and a mechanism to press down at a certain force, and at the end of the metal rod, we attach a tip. And this tip is of a certain type of material and hardness itself. And so we press this pointed tip into the metal, and we measure the depth of the tip, and the depth of the tip determines the hardness. If it's very shallow depth, then the tip couldn't penetrate the metal very far, and thus it's a harder material. And if the tip goes further, then it's a softer material. Okay, so that's how a hardness tester works. So we've got two tips. They'll fit on one machine, and they suspect that one of the tips is giving a different value than the other. Okay, so the first option is we could run a complete randomized design. Basically, we'd take 20 metal specimens or coupons. These are called coupons. We could randomly select those. Half of the specimens would be randomly assigned to tip 1 and half to tip 2. Now, the specimens, but what if the specimens are from different heats or batches, which in most cases, let's say they are. Then different heats or batches are not necessarily homogeneous, okay? So this would be a bad design in this case, because we would have an unintended inflation of error due to material variation. Okay, so that would be included. Okay, so we want to get rid of that. So our other option is if we have the hardness coupon large enough to handle two different hardness measurements. So then we would divide the coupon into two halves and randomly assign one tip to one half, and the other tip then would go to the other half. All right. And the order in which the tips are tested for each coupon would also be randomly selected. And what we're doing here is blocking out the material variation. So again, the issue is that the metal coupons differ slightly in their hardness. And the coupons are the experimental units. And this each experimental unit, if we use a random block design instead of a completely random block, completely random design, sorry, not a random block design. If we don't use the CRBD, then the variation from the material will be, it will inflate the experimental error, or sigma squared. Sigma squared will be inflated, okay? So again, the solution is to block by material. And what we'll do is we'll test each tip on each coupon. And so now we only need 10 coupons. Okay, so 10 coupons total. Okay? And it doesn't take a lot of area for us to be able to test hardness. So this means that we can use the same size coupons we were planning to before, but now we only need 10 of them instead of 20. Okay? So each block contains both of the measurements of, or the measurements of both tips, okay, or treatments. And in other words, each block, we consider each block complete and homogeneous. It's complete because it has all A, or in this case 2, measurements on it. And in a small coupon, the hardness won't vary very much at all. It might not even be measurable, okay? Within each block or coupon, the order of the treatment is randomized. So again, we'll label side 1, side 2, and then we'll generate randomly for each of the coupons which side gets block 1 or tip 1 and which side gets tip 2. Okay? So a complete randomized block design, we're going to block by the nuisance factor. Each block contains a measurement for all A treatments. Okay? The blocks are chosen in random order, and this usually occurs naturally, but I'll emphasize usually, make sure that they do. And then the measurements on each block, the A treatments, are in random order. So if you have more than 2, then you'll divide your block up into A different parts and maybe label them 1 through A. And then you'll generate the randomness with which you'll say you'll choose, say, 1 through A each time. For each block, you'll choose 1 from that, and that'll be the first one. And then you'll choose you'll choose all A of them, but without replacement. And then that will be the order, and that will be the in order. Tip 1 will go to the first number, that zone. Tip 2 would go to the second zone. Tip 3 to the third zone. So let's say that we had something that had 4 sections. So we'd call this 1, 2, 3, 4, and so we generate a random order, let's say 4, 1, 2, or 3, 2, okay? And so this number would go with tip 1, this would be tip number 2, this would be tip number 3, and this would be tip number 4, and so tip 1 would go to 4, so this would be tip 1, and we said tip 2 to go, so tip 2 would go here, and tip 3 on this block would go there, and then tip 4 would go to number 2. So that's what I'm talking about, okay? So that's an example. So we have some advantages. So it's important for you to know the advantages and disadvantages of this method. So the advantages are that generally this is more precise than complete random designs, okay? These results are more precise because we're breaking out the error for the blocks and taking that out of the error either for the treatments or for the residuals or random error, okay? So we'll take the variation, out of that. There's no restriction on the number of treatments or replicates, okay? Some treatments may be replicated more than others. We may have an unbalanced design, and that's okay. We can do that. Also, we can handle missing data, and the analysis is still relatively easy. In fact, we can delete whole treatments from the analysis if we need to and still handle the analysis. And here's a big one. If we don't have equality of variances, we can still make valid comparisons. This is really important here. Okay? So what if you have different, for the different treatments, you have different variances. Heterogeneous means different. not homogeneous, so which would mean the same. So so we could still have valid comparisons even if we violate the equality of variance assumption. Okay? The disadvantages. The error degrees of freedom is smaller than it is in the complete random design. That makes MSE larger. However, that does make it look larger, but we're also taking error out to the blocks. We're partitioning the error into the variation into 3 portions instead of 2. 1 for the treatment, 1 for the blocks, and 1 for the error. So even though this is smaller, it's not that bad of a disadvantage. Okay, it's not suitable for a large number of treatments. Even though theoretically we could have as many as we want, this may create a need for the blocks to be too large or impractical to handle. Okay. It can be less efficient than the complete randomized design if we have data missing, and this is a maybe. Not always, but maybe. But it's something to know and something to be aware of. If you have missing data, you need to be careful. Okay, you may have less efficient results. It's not suitable if the block contains considerable variability. What does that mean? That if we divided the block up into portions, and from this end, the variation, the average here is very different than the average here, then that wouldn't be an appropriate block. And so this would not be a good method. It's not suitable. This is not a suitable method if the block contains too much variation between the different zones. Okay? And then the interactions between block and treatment effects can increase our error if that exists. So if this exists. So that's something that we would want to test if it's possible. Okay? So the most important consideration for the complete randomized block design is that we need a uniform experimental unit. So we don't want a lot of variation across this coupon if we're talking about the hardness tester situation, or across the block if we're talking whatever we're talking about. Okay, so the block needs to be as homogeneous as possible. Okay, so we're going to talk about the first model in this video, and this model will have no replicates, so there can be no calculation of interaction. Okay, doesn't mean the interaction doesn't exist. It just means that you can't measure it. So we're going to have A treatments, and we're going to have B blocks, and we're going to have K equals 1 replicates within each block. There's no replicates, so it's impossible to calculate the interaction. So here's our model. It's going to look a little different. Now we have Yij. We don't have K here because K is just equal to 1, so there's no need to add another subscript. But we do have to add this term for beta j, the effect of the block. Okay, so we have mu, which is the overall mean. We have tau I, the effect of the ith treatment. Beta j is the effect of the jth block, and epsilon ij is the random error. And epsilon ij is normally and independently distributed with mean 0 and variance sigma squared. This is our random error. Okay. I goes from 1 to A, J goes from 1 to B. Case 1, we're going to have fixed effects for both of these. Okay, so fixed effects, and that means that the assumptions that we have is that the sum of the tau i's is equal to 0, and also the sum of the beta j's are equal to 0s. Now, what are we going to test here? If we have a fixed effect, we're going to test tau 1 equal to tau 2 equal to tau 3 up to tau a, and all of those are equal to 0. Okay, if they're all equal, they have to be equal to 0. Remember that tau I, tau I is different now. It's going to be mu I is going to be equal to tau I plus beta j, tau I plus beta j plus mu. Okay? And so tau I is going to equal mu I minus beta j minus mu. Okay? So if these are all equal, then they all have to be 0, okay, because they're a subtraction here, okay? And the alternative is that at least one tau I is not equal to 0. Then, or we could use the means model and say mu I is equal to mu1 is equal to mu2, etc. is equal to mu A, versus at least one of the pairs, mu I, is not equal to mu J. So at least two means are different for I not equal to J. So those are our hypothesis statements. And so here, I'm sorry, I left out a subscript, mu ij. Mu ij is mu plus tau I plus beta j, okay? And to get mu I, we would have to sum over the j's and take the average. So we're going to say j equals 1 to b and then 1 over b of this. And what do we get here? So I have 1 over b here, and then I have sum of mu from j equals 1 to b, plus the sum of tau I from j equals 1 to b, plus the sum of beta j from to b, j equals 1 to b. Now, look at my assumption here. The sum of beta j's is 0, so that's 0. And so we get 1 over b, and then we'll have mu doesn't have a j subscript, so we're going to have b times mu. And then the same thing for tau I. It doesn't have a j subscript, it has an I subscript, but we're not summing across I, we're summing across j. So we're going to have b tau I, okay? And then this will equal 1 over b times b mu plus 1 over b times b tau I. So we're going to equal with mu plus tau I. Okay. All right. And so this is what mu sub I is. It's equal to mu plus tau I. Mu I. Okay. And that makes sense. That's exactly what we had before. Mu plus tau I. Okay. Now, let's look at some notation here. And so we have mu yi dot. This is the sum. This is not a mean. I don't have a bar here. So we're summing over. So we have yij. If we have a dot here, that means we've summed over this second indice. So that's going to be the sum from j equals 1 to b of yij. Now, y dot j means that we've summed over I, which is the first, I is the first indice, and we have a dot. That means we summed over that. This is the sum from I equals 1 to a of yij. We're just summing over the y. And then y dot dot means that we've summed over both. We've summed over I equals 1 to a and j equals 1 to b of yij. Now, to get the means, we only have one replicate, so we don't have to worry about k. So we just have 1 over a times yi dot, which is 1 over a times the sum of yij from I equals 1 to, or j equals 1 to b. Okay, so 1 over b, I'm sorry. We've summed across the j, so we have to divide by b, not by a. Okay, and then y dot j is 1 over a y dot j, or 1 over a sum I equals 1 to a of yij. And then y dot dot bar, we have 1 over a times b, or n, times the sum over both yij from I equals 1 to a and j equals 1 to b. Now, the ANOVA, we are going to talk about analysis of variance. So we're taking the variation SST, and we're now going to partition it into SSTRT, the treatment effect or variation, the variation or sum of squares for the blocks plus the sum of squares of the errors. And so SST is can be written as the sum, double sum, of yij minus y dot dot bar squared. And I goes from 1 to A, j goes from 1 to B. Okay? And then if we partition this, I won't go through it, but what we're going to do is we're going to add and subtract some things within the square. We're going to actually add and subtract yi dot bar and y dot j bar and y dot dot bar. Okay? And is that right? No, we don't. We just add and subtract y I dot bar and y dot j bar. And then we reorder them, and then it turns out that the cross products all cancel out to 0, and so we're able to write this as a sum of 3 things. And so SSTRT is going to be the sum, B times the sum of I equals 1 to A of yi dot bar minus y dot dot bar squared. So this is the sum of the differences of the treatment means from the overall mean. Just like we had in the one-way ANOVA, we had yi bar divided by or minus y dot bar, right? And then the sum of squares for the blocks is A times the sum of j equals 1 to B of y dot j bar minus y dot dot bar quantity squared. So this is the block treatment, or the block means minus the overall mean. Those differences squared and added up. And when we sum across A, there's no subscript I there, so we just multiply the whole thing by A. And then SSE is quite a bit messier, but let me show it to you. We usually don't calculate this. We usually calculate all the others, SST, SS treatment, and SSB, and then we'll take SST minus SSTRT minus SSB, and that's a lot easier than calculating this directly, and you'll see why. It's the double sum of yij minus yi dot bar minus y dot j bar plus y dot dot bar quantity squared. Not a small calculation here. So it's much better to let a computer do that for us. All right. So these 3 add up to SST. Okay? So we still have that partitioning of the sum of the total sum of squares. Now, I'm not going to go through the derivation. I'm just going to give you the answers here. So we have sigma squared plus b times the sum of tau I squared, and this is I equals 1 to A, over A minus 1. And what we can say that this is equal to sigma squared plus b sigma a squared, where we are calling sigma a squared this b times the sum of tau I squared over A minus 1. It's an estimate for that, but it's not really a variance, but we're notating it like it is. And then the expected value of the mean square for the blocks is going to be sigma squared plus A times the sum from j equals 1 to B of beta j squared over B minus 1. And again, we're going to call this sigma squared plus A sigma B squared. Okay, so I need to take out this B up here because I have the B right here, okay? And then for this one, this means that sigma B squared is going to be the sum of beta j squared from j equals 1 to B over B minus 1. Again, this is not a true variance in this case, but we're going to do this so that when we look at the random effects model. Next time, we'll see a similarity. Okay? And then the expected value of the mean square error is sigma squared, so unbiased estimator. And f of A is going to equal the ms of TRT, the treatment mean square, divided by the mean square error, just like we had before. So we're not dividing it by anything else. We're going to divide the mean square of what we're wanting to measure by the mean square error in this model. Okay? And so now we have our ANOVA table. And I've written out the computational formulas in case you want them. I'm not going to ask you to compute these. We're going to let the computer do that for us. But we do have the treatment sum of squares, that calculation here, the block sum of squares here, and then error. Notice I just say subtract these other three because that's just too much calculation, even the computational formula. And then down here, the computational formula for the SST. This will be SSE, and this will be SSB, and this is SS treatment. The degrees of freedom, A minus 1, B minus 1, N minus 1, which is AB minus 1 in this case. And if you take AB minus 1 minus A minus 1 minus B minus 1, you can rearrange this and see that it's equal to A minus 1, B minus 1 if you factor it correctly. So a little bit of algebra will get you there. So that means that you can add up these degrees of freedom given here and get capital N minus 1. Now, the mean square, we have a mean square for the treatment, SSTRT divided by A minus 1, and for the blocks, SSB divided by B minus 1, and for the error, SSE divided by its degrees of freedom. And then we have, this is F of A here. But the next one is for the blocks, but you're going to see that there's two different viewpoints on this, but I'm going to give you the recommended. Anybody who subscribes to this being a valid test probably doesn't know a whole lot about statistical theory, okay? So this is going to be MSB divided by MSE, and we call that F sub B, but computers spit this out because they do everything the same way, and they're programmed to always do this in the ANOVA table. But it's not a meaningful. It's not meaningful as an actual test. So there's a reason for this. The blocks represent a restriction on the randomization. We're restricting how we're randomizing this design. Instead of a complete randomized design, it's a complete randomized block design. So this block is restricting our randomization and not allowing us to have complete randomization. And so it's not a justified test. So if the errors, let's see, it says that, so some people believe that it's a meaningful test, but again, you've got this restriction which really makes it, when you think about it, it's not randomized. It's a restriction. So it just doesn't make logical sense. You can't really look at this and say what it exactly means. So the book tells us that it's not a good practice to use this as a test to say that the blocks are different from each other. What we can do is we can determine if the blocking was useful. If this ratio is larger, the larger it is, then the more effect the block has on the results, and there's a noise reduction, a bigger noise reduction obtained by the blocking. And so it was helpful in improving the precision of the comparison of the treatment means. So it makes a larger F of B makes the test f of a more precise. I can't use the word accurate, but at least more precise. There's less variation. Why? Because instead of this being in the error, it's now taken out of the error, so the ratio of MSTRT to MSE, the MSE is going to be smaller, and so this gives a better picture of the real variation due only to the treatment and not to the material in our example or to whatever the block is in other examples. Okay, so that's it for this video. We'll pick up here next time. If you have questions, please come to virtual office hours. If you have questions that need to be answered before then, email me. If it's about a problem, make sure you give me the picture of the problem in your email plus your work so I can see what the problem is and see how you're approaching it and help you better. Please take care of yourself, stay safe, because we hope to see you next time.